I'll show you here. We've got some insulation materials. We've got a wood fibre there. The white one's polyester, and that's another wood fibre. And then usually this takes about 20 minutes to do 4 products. So we do the tin, polyester, an EPS foam, and the wood fibre. But I've left those results on just to save time. So while we're doing the other 2, it'll take 10 minutes to do that. We'll go through it. So what we'll do, we'll start with the polyester. So it's a 90mm polyester bat. And then I'll take a reading on the surface using a laser thermometer. Take the reading at the surface, a reading at the back, put the results on here, and then every 2.5 minutes, we'll take another reading to see what happens. So let's set this up.
So you're putting that in front of a heat lamp, right?
Yeah, so we've got an infrared heat lamp, and it's about 200mm away from the lamp to the surface of the polyester. So that's currently 24 degrees at the start. On the face. On the back, 23.7. Okay, so now turn the lamp on. You can see that, okay, nice and bright. Then we talked about this, Daniel, how we'll take a reading of the heat source if we can. Bit difficult to get. It's already 70 degrees, between 60 to 70 degrees on that.
Yeah. So I probably would do that at the end when the light was on for a while. Then you probably get better reading on that.
2.5 minutes. So is the tin. That would just be corrugated roof sheet like that. And this is to show what we would call the decrement delay, or how long it takes for the heat to pass through the material. So with the tin, it starts at 25, see 25, 24, the foam was 27, so they're all about the same. But after 2.5 minutes, the tin had increased on the surface to 74.7 degrees. And on the back, after 2.5 minutes, it had gone to 69.1. So about 3 degrees difference from the front to the back only after 2.5 minutes. And then at the end of the experiment, you can see the tin on the face had gone up by 48 degrees. But on the back, it had gone up by 49.7. So within 5 minutes of the heat hitting that tin, all that heat had passed through. So that's partly why you get the overheating issue in the Australian houses. So that was that one. The foam didn't actually increase more than the tin. On the surface, it went to a total of 58 degrees on the surface. And on the back, it only increased by 3.2 degrees. And in the experiment, I usually say, oh, that's good, isn't it? And people go, yeah. And it is good because it's an insulation material. That's kind of what you'd expect. But the foam isn't vapor permeable. So then you get another issue that needs to be addressed. So it's not just as black and white as, oh, let's just work on some good insulation.
So do you have an idea why the foam gets hotter on the front than the tin?
You'll be able to give us a good answer for that.
Yeah, I think it's just because the tin is like a radiating fin on the outside. So it absorbs more heat to the outside. So it sucks the heat quicker out. So the ambient situation, I think, is absorbing the heat. It goes into the tin to the sides, and this is already working as a cooling fin. Yeah, and that's the reason why it's not getting so hot. And that's probably the reason why the front is not getting that hot. And
also the tin's only like 1.5 millimeters thick, whereas the EPS foam 60 millimeters. Going. So let's reset that. Okay, got it. Now start again. So 2.5 minutes in. Surface of the polyester 86.
86, yeah.
Polyester on the back. 30.
30. So that's not too bad, isn't it?
30.1. Yeah. And actually, just as an interesting note, the R value of that polyester is R2, and the wood fibre is R2.55 that will do. So
okay.
it's
so the wood fibre is a bit better than the
but actually the 60mm one, that's the one that I usually would use. That's got a lesser R value. The R value is only R1.45.
Yeah. So should we use that one, because that should be in like working against wood fibre?
Yeah.
If you're using a better wood fibre board, then obviously we have to expect a better result. But if you're using the worst wood fibre, like the higher density one that you have from a U value perspective, so probably want to use that one this time just to see how it is actually performing.
Yeah. And that's people always say, what's the R value? Yeah. But the return question is it really R value? There's a lot more to it than that.
Yeah. And we'll discuss that in the member section, what is actually bringing that result. Why is a poorer R value? Why maybe a poorer R value is performing better? We don't know the result yet. The experiment is not finished. So So let us leave it at that. So
the time is gone.
Timer.
After 5 minutes, the surface of the polyester is 90.1. On the back side, $34.1. Okay, turn the lamp off. Let's set that to one side and then set up the wood fibre. I'll just quickly show you the differences. That's the 90mm bulk infill. So that's an R2.55.
So that's for between the studs, right?
Yes, correct. And that's got a lower thermal conductivity at 0.036.
So it's a better thermal insulator than the one that you're showing us now.
Yeah, this one is astronomically higher density. That's got a density of 60 kilograms, whereas that polyester bat has only got a density of 20 kilograms.
That high? Okay.
Yeah.
Because fiberglass is 10 kilos.
Yeah, it might not be that. That's all it could. 20's the positive side of it, I guess.
Yeah.
This one's got a density of 185 kilograms per meter cubed, and the R value of this is R1.45.
So, and that's now a board that is installed on top of your studs, isn't it? Like you're having a 90mm stud, you fill in your infill insulation, and then on top, you're installing that with some screw fixings or something.
Yeah. We can go through that detail on the model there at the back. So, temperature reading on that is 24 degrees.
Okay, so it's the same than your polyester.
Yeah. 21 degrees. We put the heat on straight away.
Okay, you think that the heat already heated up the front. Yeah, that makes sense.
Yeah. So turn that on. Okay, start the timer. Off we go. The timer's going. Go on the surface. 71.7. On the back. 21.2.
So it didn't really go. It even went down.
It actually went down. Yeah. So that's why this isn't a controlled experiment. We have to caveat in there.
So how are you messing with the numbers there, James? What are you doing?
And it's live. It's on camera. No doctor.
Oops, temperature went down. That's not good.
Yeah.
But like theoretically, it could be actually evaporation, like that there's moisture in the board, and that actually is the heat now pushing the moisture through, that actually the temperature could drop in that 2.5 minutes time frame. So like I'm making that up in a way, like it's an explanation I have if that is really the case, that the temperature dropped, but it could be the evaporation of moisture off the board actually letting the temperature drop. So it might be actually correct, even it looks really weird.
Yeah. The surface is 88.2. The backside 21.3.
So it went up at least from the 2.1 minutes,
Yeah.
2.5 minutes.
So now we just need to do some quick maths, I guess. So let's calculate. I'm rubbish at quick maths. So the polyester on the surface increased by 66 degrees versus the wood fibre, which increased by 64 degrees. On the backside, after 5 minutes, the polyester increased by 10.4 degrees, and the wood fibre was actually 0 or a negative.
Negative by 0.4.
Yeah. So what's crucial about that is when you look at the bigger time scale, we generally see the polyester performs and gives you about an hour of delaying the sun's heat passing through, whereas the 60mm board on its own gives you 4 hours, and then the 90mm flexible infill also gives you 4 hours. So as a combined system, we're seeing 8, and when you put in the ventilated cavities and the rest of the wall build-up, we see 8 to 10 hours, which is the reason why it really saves energy is the term that I would use.
So in other words, so we're having now the situation with polyester and wood fiber. They got nearly to the same temperatures on the external side of the building, but we don't really care about that temperatures. Even like your 48 degrees or 58 degrees, we're not really worried about that side. That's outside of the building. What is really interesting, what actually arrives on the inside, and that's what we see, like the tin went up by 50 degrees, the polyester by 10, and the foam by 30, but the wood fiber stayed at 0. And that's this time delay of the heat transport. It needs some time. And that I think is like the U value calculation that we do, or the R value, that tells us what's the maximum load that comes through. So how much energy comes through if you're having that heat lamp or the sun burning on it for, say, 20 hours. Then that load is not changing any longer. Like the amount of energy that comes through is not changing. It's not telling us when that actually comes through. And that's where the density of the wood fiber comes in.